Hello, everyone. Welcome back to the interactive sessions on circular dichroism and Mossbauer spectroscopy. So, this is our ninth interactive session, and we have been discussing about this Mossbauer spectroscopy from last class, and today also we will be continuing with the basics of the Mossbauer spectroscopy, how the technique originated, what is its instrumentation, and for what kind of systems we usually record the Mossbauer spectroscopy, and what could be the possible applications of this spectroscopic technique. So, okay, let's get started with our today's session. So, in the last class, we discussed about the recoil energy. So, if you remember, I will be repeating it again today, so that uh, it's just a simple revision of the basic concept. So here we are taking a source, a nuclei 1 as source, which is already in its excited state. And when the system is in its excited state, the source is in its excited state, and when it is going back to its ground state, it emits gamma radiations. From its I equal to 3 by 2 nuclear state to its ground I equal to 1 by 2 nuclear state. So during this transition, it is emitting gamma rays, and these gamma rays are further absorbed by the sample for its transition from ground state to excited state. And the best thing and the good thing here is these both source and sample are same 57 Fe atoms. So, what is the difference involved here? Why we are looking into the emission of gamma radiations from the source, and these are being absorbed by the same sample? There must be a difference present over here. We will be discussing it in few minutes. So, and during this absorption of energy by the sample, there is again a recoil energy involved. And because of this recoil energy, because of loss of recoil energy by source and gain of recoil energy by sample, E transition is not equal to the energy of gamma radiations emitted and absorbed. E gamma is equal to E transition minus E recoil energy, that is loss of this recoil energy by sample source sample, and this recoil energy is gained by the sample. So, in the last class, I gave the example of a person who wants to jump from one boat to another boat. So, when this person is jumping from one boat to another boat, the boat from which it is jumping, it will experience a pushback, and the boat which is also from to which the person is jumping, it will also experience a pushback in the opposite direction. That is, both boats will be shifting back from their original positions, and one of them will be losing the momentum and other will be gaining the momentum. That is, the momentum will be balanced. But this is happening when this system from where the person is jumping, that that is lower in mass, when the same jumping of process is being when this jumping process is being done in a heavier ship, then in that case there will be less recoil energy, that the amount of pushback being this recoil loss and gain observed between two ships will be very less. So in that case, and also I give the example of gun. When we fire a gun, we when in case we fire a gun, we experience a pushback in our shoulder, and that is because of the reason that we are trying to maintain a momentum. And that is the reason in this case also, when this sample when this source is going through a transition, that is from excited state to ground state, it is losing the energy in the form of recoil energy, and this energy is gained by the sample when it is absorbing the same gamma radiations from from its ground state to excited state. And this is happening because this atom is very when we are observing this transfer of energy from source to sample, these samples are very less in mass, that is their weight mass is less, and that's the reason they are experiencing recoil energy. And to avoid that recoil energy, we introduce the concept of putting these nuclei in the crystal lattice, and in that case the overall effective mass of the source and sample will be increased, and that will help us in reducing the loss of energy in the form of recoil energy. So Because of this, the energy transition from source and sample, if we record the absorption spectra for this, we will observe a difference in their maxima of energy absorption, and there will be a poor overlap between the two. This is the overlap reason for energy transitions. And because of this, there is a loss of energy during the whole process, and we are unable to find out how the this energy is being transferred to the source, from the source to the sample. And due to this reason, this spectroscopy technique becomes very impractical. To avoid the loss of recoil energy, Rudolf Mossbauer introduced the idea of putting these source and sample nuclei in a crystal lattice, in a solid matrix, we can say, in a solid crystal matrix, which will increase its overall effective mass and hence a decrease in recoil energy. And now, when this source emits the gamma radiations, which will be absorbed by the sample, which is also embedded in a solid matrix, then recoil energy is decreased, this process is called recoilless event. And this reduces the energy gap and hence better overlap between source and sample transition bands. And this is the only recoil energy loss involved in both the transitions. Now, in Mossbauer transition, in Mossbauer spectroscopy, transition from one nuclei to another nuclei is possible, but not among all of the, like, we have so many elements in the periodic table. If we have to take a source and sample, for example, here we are taking 57 Fe. So. Are there all the elements able to, like, are all elements active for this Mossbauer spectroscopy? Are all these in Mossbauer spectroscopy we have to take care that transition from nuclei to another nuclei is possible, but not among any two nuclei. There is only few nuclei in the periodic table for which this transition nuclear transition is possible, and the condition for that is, in Mossbauer spectroscopy, transition from one nuclei to another nuclei takes place, is involved, but not all nuclei in periodic table can undergo a Mossbauer transition. That is, not all elements, or we can say their nuclei are Mossbauer active. So, nuclear resonance absorption can only be observed when the difference of transition energy and emission are similar to the sum of line width. So only those nuclei for which the sum of line width of the absorption band, transition energy band of source and sample are similar to the sum of their line width, then only a nuclear transition will be possible. And let us discuss what is this line width. So when we record an absorption spectra, we generally observe this kind of absorption band. So this is kind of broad Lorentzian shape band we generally observe in absorption spectroscopy. So the question is, why don't we observe a single line? Because this transition is taking place from ground state to excited state, and we have a well defined transition states for the sample. Then why this kind of broadband? Why for this single transition we are not getting a single line with single line in the absorption band? Why don't we get a line band in the absorption spectra? This is kind of the line band we expect, but this is the kind of Lorentzian band we generally obtain. And this is line width of Lorentzian band. This is basically 50% absorption at maxima. This is basically, so if we consider that this is the maxima, this is the energy, or we can say this is the wavelength which on for which we are getting the maximum intensity. So we will find out the 50% of this absorption at this maximum wavelength, and we will calculate, then we will find out the width of this peak at the 50% of this absorption maxima, and this is what we call line width. So we observe this broad Lorentzian profile because of Heisenberg uncertainty principle. This line width is represented by this symbol. And what is Heisenberg's uncertainty principle? The probability of finding the position and momentum of a particular system, let's say electron, uh, the probability of finding both the position and that is, we can't find the position and the momentum of a particular system, let's say electron, precisely at the same time. Uncertainty in position, in momentum. It says that we can't define both position and momentum of a particle precisely. Because if you see, if you are saying that you are fixing the position of the particle at uh, this delta x is nothing but position, or we can say space dimension. You can say space dimension, and the position dimension are x, y, and g. So if we are defining this delta x, that is this its position to be 0, then the momentum, which is based on the time, which is based on fourth dimension, that is time cannot be defined precisely, as this momentum will be infinite, or we can say undefined. So at particular time, if momentum is going to be 0, then its position will be undefined. And similarly, if we fix the position, then the momentum of the particle will be infinite or undefined. So there has to be some uncertainty such that if we are defining position of a particle at some place, then its corresponding momentum is reported with some kind of uncertainty. So we are finding them together, but with with some sense of uncertainty in their positions and momentum. And such variables are called complementary or canonically conjugate variables. It means if we have two parameters which can define all the different dimensions, and how many dimensions we have in total? We have four dimensions. Three are position dimension, which is x, y, and z dimension, and the fourth one is time dimension. So it means if we have two parameters which can define all the different dimensions, then all the different dimensions possible to explain that particular system will be known as complementary or conjugate variables. So there will be always two variables involved. One of the variable will define the space dimension, that is position xyz dimensions, and one of these variables will be defining the time dimension. For example, in this Heisenberg's uncertainty principle, we have delta x into delta p, two variables involved. One is position variable and the other is momentum variable. So simply, this position variable is defining xyz dimension, and this momentum is based on the velocity of the system, and again then velocity is based on the time dimension. So here these four dimensions are involved in this particular principle, and which are complementary to each other. So if you are able to find out the space dimension, you won't be able to define the time dimension of that particular system. So we have like from our school level studies, we have just learnt about this uncertainty in Heisenberg's uncertainty principle. The only two variables we know till now are that of position and momentum variables. but there are similar or conjugate variables as similar to this Heisenberg uncertainty principle, which are energy and lifetime variable, which also follows this complementary which are also canonically conjugate variables. A similar or conjugate variable as Heisenberg's uncertainty principle are energy and lifetime variable. Energy and lifetime, that is delta t variable, which are also complementary variables. So in this we have delta x into delta p variables involved. But we so we have other conjugate variables, which are energy and lifetime variables. Now, what is this lifetime variable? This delta t lifetime variable is nothing but how long a particular system is going to stay in its excited state, and that depends on the energy gap between the ground state and and excited state. So this is energy gap between these two states, and delta t is the lifetime, the time which this particular system is going to spend in the excited state. So if the system is going to stay for a longer period of time in the excited state, that means its lifetime is more, then its energy gap will be lesser. So these are complementary to each other, or we can say reciprocal to each other. So we have a new attendee. So hi, this Priyosmita. Can you hear me? Do you have any doubts?
Yes, I can hear you, and no, I'm understanding quite well.
Okay, are you following these sessions?
Uh, no, I'm not being able to follow all sessions, but few of them are.
Okay, great. Okay, so I'm continuing. If you have any doubt, you can ask or you can write in the chat box also.
Okay, okay, sure.
So this is how long a particle is going to stay in the excited state, and that depends on the energy gap. So if lifetime is high, which that means energy gap is less, and vice versa is also true. So if we correctly understand this uncertainty in the lifetime and the energy gap of a particular transition, if this delta E is equal to 0, that is the energy gap between the excited state and ground state is 0, so which is not the ideal case, but for that case we will get a single line in the absorption spectra. But this is not the kind of spectra we usually observe. What kind of spectra we get is this Lorentzian shape band. So delta is equal to 0 is for a perfect single line in absorption spectra, which means system will always stay in the excited state for forever and it doesn't come back to the ground state. That is, its lifetime is infinite, and this is the reason we never see a straight line between we never see a straight line, but always a broad Lorentzian band in the absorption spectra is observed, as there will be some finite lifetime, that is the particle can't stay for forever in the excited state. The amount that particular lifetime will always be finite, and if that is finite, then uh, this energy gap is also going to be finite. So if delta E is going to be 0, that means delta T is infinite, that is it is undefined. Particle will forever will forever stay in excited state. But this is where this uncertainty in energy and lifetime equation comes into account. So this says that we can't precisely define both energy gap and lifetime of a particle. There is always going to be finite energy gap, and therefore finite lifetime. And that's why we get this Lorentzian shape band, for which we can say that delta E is not equal to 0 and delta T is not equal to infinite. That is, both of them are finite numbers, or we can say we can precisely we can't just say that one of them is 0 and another one is infinite, but they will have some certain value. And this delta E energy gap is equal to life this line line width by 2. Line width is nothing but half absorption at maximum. So basically you will just find out the maxima of the band. If this is lambda max, then you will find out the half intensity for this particular band, and you will find out the width of this peak, and this is what we call line width. So if delta E to delta, if we say this is equation 1, and we have this is this uncertainty equation, and we substitute delta E, we will get that this line width, that line width will never be equal to 0. That is, we won't get a single line, in the absorption spectra. Means we are going to see some line width, and hence hello. uh, okay, I'll try to can you hear me now? Hello.
Yeah, I can hear you. Yeah.
Okay, I was just writing, so maybe because of that you can't hear my voice. So hence in this case, hence there will be finite lifetime. So for Mossbauer spectroscopy, we generally take 57 Fe nuclei, and for which we consider this transition, nuclear transition from I equal to 3 by 2 to I equal to 1 by 2. And this, and for this transition, the lifetime is equal to 141 nanosecond. That is lifetime of this 57 Fe nuclei in I equal to 3 by 2 excited state is 141 nanosecond. And from this, if we find out the line width of the absorption band, it will be equal to S direct by delta T. So it is going to give us this value 5 into 10 raised to minus 9 electron volt. This is the line width. It is this line width will be equal to 5 into 10 raised to minus 9 electron volt for this 57 Fe nuclei. So now if you try to find out the line resolution, that is equal to line width divided by energy. We can say energy gap. So it is equal to 5 into 10 raised to minus 9 electron volt divided by 14.4 into 10 raised to 3 electron volt. So the energy gap between these two nuclear state is 14.4 to 10 raised to 3 electron volt, or we can say 14.4 kilo electron volt. So this line resolution will come out to be 3.3 into 10 raised to minus 13 electron volt. So the main thing you have to observe here is the order of this resolution, that is 10 raised to minus 13, which is very low resolution. So this 3.3 into 10 raised to minus 13 electron volt is very low resolution, which means in 14.4 into 10 raised to 3 electron volt energy gap, we are trying to find out the shifts in the energy bands on a resolution order of 10 raised to minus 13 electron volt. It means not all isotopes can show good signal. Then what makes a particular nuclei Mossbauer active? And if we draw a comparison between optical spectroscopy and Mossbauer spectroscopy, for which if you compare the line width, energy gap, and the line resolution, the order for the order of line width for optical spectroscopy is 10 raised to minus 8, and the energy is 0.121 electron volt, and resolution is 10 raised to minus 7 to 10 raised to minus 9. However, for Mossbauer spectroscopy, it is 10 raised to minus 9, 10 raised to 4, and 10 raised to minus 13. So, when you record an absorption spectra uh, in the optical spectroscopy, uh, we are measuring a shift on an order of 10 raised to minus 7 to 10 raised to minus 9. So in that case also we kind of face a difficulty to like on some level we face a difficulty in observing that particular shift, because we get a Lorentzian band, that is a broad spectra, and in that case if we have a sharp band, we can clearly observe this shift in the spectra, the shift in the band. But in the case of broadband there is some kind of errors involved. If we face this difficulty on a scale of 10 raised to minus 7 to 10 raised to minus 9, just imagine how difficult it is going to measure any shift on an order of 10 raised to minus 13. And that is the reason, because of this poor resolution, we have to consider only certain nuclei, which for the Mossbauer spectroscopy, it means we need to have a system that measure a change of lambda on an order of 10 raised to minus 4 difference, lesser than optical spectroscopy. So we need to have to this resolution to be high for Mossbauer activity, and for this line width should be high value, and this energy gap should be low, and this will make the resolution for the Mossbauer spectroscopy spectra to be very high. So what are the conditions involved here? Condition 1, excited state. So this line width is inversely proportional to lifetime. If this lifetime is going to be uh, less, if lifetime is going to be less, then this line width will be high. So the condition one is excited state lifetime should be less, should be less for high resolution. And the second condition is this energy of transition should be low. For this to be high, lifetime should be less, and this energy of transition should be low. So this is the periodic table which is showing these blue colored elements are Mossbauer active, and this value is showing that the number of isotopes in which the Mossbauer effect has been observed. That is for a particular element. That is for iron, it is 56 Fe and 57 Fe. So there are two isotopes of iron possible, and its 57 Fe isotope is Mossbauer active, and that is why this value is 1. And for and it is also mentioned that is the number of observed Mossbauer transitions for a particular element and its isotopes. So this is the table, but out of it the elements which have been studied for Mossbauer spectroscopy are: first is 57 Fe isotope, which is most commonly studied, or we can say most commonly used in spectroscopy. Then it is 119 tin, then 121 antimony, fourth is 129 indium, and fifth is 197 gold. So these are some of the elements which have been studied for Mossbauer spectroscopy, but the most common one is this 57 Fe. Okay. So now we will take a look into 57 Fe based Mossbauer spectroscopy. So this 57 Fe isotope is not very naturally abundant. The naturally more the its 56 Fe foam is more abundant in the atmosphere. So in the ecosystem, we can say. So the natural abundance of this 57 Fe isotope is 2.14%. So to study this particular nuclei, it is usually artificially enhanced, like enrichment is done for the sample. Artificial enrichment of sample is done before analysis. Before analysis. So, so now for the Mossbauer spectroscopy, we have a source which emits gamma gamma rays on its transition from excited state to ground state, and these emitted gamma rays are used by sample for its excitation from ground state to excited state, and both the source and sample are 57 Fe nuclei. And uh, and this is the condition for this gamma rays, like the gamma rays emitted from the source, to be absorbed by the sample. Both the source and sample should be identical, and then only such transfer of energy will be possible. But then what is the difference involved here? If we are taking both source and sample to be this 57 Fe, then why are we studying such kind of systems? And the question which has been in your mind till now is how your source, how the source of Mossbauer spectroscopy is in excited state and emitting gamma radiations on transition into its ground state. And how do we get this 57 Fe isotope? So Mossbauer spectroscopy actually originate from this 57 cobalt parent nuclei, which undergoes a nuclear reaction, that is a radioactive decay, to form this 57 Fe isotope. But is this 57 cobalt naturally abundant? As it is radioactive, since it is radioactive, there must be some of its source. It is not it is not like we are getting it anywhere, like we can find it directly in our ecosystem. It must be part of some radioactive process. So this 57 cobalt is radioactive, and it is prepared from naturally abundant 56 Fe element nuclei sample by bombarding it with deuterium. This this 56 Fe nuclei is bombarded with deuterium to give out this 57 cobalt, and in this process it emits a neutron, that is particle with this 57 cobalt is emitted along with this neutron, and this deuterium is produced by cyclotron. This cyclotron is basically a type of particle accelerator which propels a beam of charged particles, mainly this protons, charged particles, protons in a circular path, and these cyclotrons are widely used to accelerate the charged particles in nuclear physics experiments, and it is and to use them to bombard the atomic nuclei. So the atomic nuclei here we are bombarding is 56 Fe, and by bombarding the deuterium which is produced by the cyclotron, we get a 57 cobalt, and which further decays from its nuclear state to the lower nuclear state to give out a 57 Fe. Charged particles in nuclear physics experiments, and use them to bombard atomic nuclei. And this 57 cobalt isotope, since it is radioactive, we can calculate its half-life time, which is found to be 270 days. Its T half is equal to 270 days, and therefore the process involved uh, is this 57 cobalt, which has a half lifetime of 270 days. It will decay from its nuclear state, that is I equal to 7 by 2, to by 257 Fe 26, and it relaxes by electron capture from the environment. So this 57 Fe relaxes to form 57 Fe by electron capture from the environment. That is, it will if there are some gaseous atoms in which this radioactive nuclei is present, it will capture electron from those gaseous atoms and leave them charged, and it will relax to give us 57 Fe. And the nuclear state of this 57 Fe is now 5 by 2. So here this is first nuclear transition involved. So this is the first nuclear transition. Now, uh, in this process, that is 57 Fe, Now this 57 Fe from its nuclear state 5 by 2 to it will go to its nuclear state, that is 3 by 2, and in the process it will emit gamma rays, and the energy of transition will be 136.32 kilo electron volt, and it will further relax to its ground state with nuclear state I equal to 1 by 2, and in this process it again emit the gamma rays, and the energy for this transition is 14.4 kilo electron volt. And this is the reason we are studying for the Mossbauer spectroscopy. And this is how a sample is in its excited state, and while its transition to the ground state from 3 by 2 to 1 by 2, nuclear state I equal to 3 by 2 to 1 by 2, it emits the gamma rays which are absorbed by the sample for its excitation, and this is the process, and the reason why the source is in its initially in the excited state. So here two gamma rays are emitted in the process. First is first is in energy. First is of energy equal to 136.32 kilo electron volt, and the second one is 14.4 kilo electron volt. And this reason is we are using for Mossbauer spectroscopy. Uh, Hi Maniratnam, are you
Hi
following?
ma'am, good evening.
Good evening. Are you following the sessions? Do you have any doubt?
Okay ma'am, just now I joined in this session just 3 minutes before.
Yeah.
Um, Already regular classes attended Saturday 7 to 9. Okay, yeah, if I have any doubt, I follow this session ma'am, no problem.
Okay, so like I have seen you have been following the Saturday sessions by Vasudha. So I just wanted to ask, is there some time issues, or are you not getting the lectures properly? Like you are not getting the content I am teaching. Is there any problem? I would love your feedback in this uh, regard. So is there anything you want to say?
Okay ma'am, no problem. Ma'am explain is in a good. Um, I
Okay.
follow the.
Okay, no problem. You can follow whatever session you are comfortable with. It's just for your uh, like to help you only. We are hosting these sessions. So okay, I will continue with my. Uh,
Okay ma'am.
so now, how the experiment is done? Like, what is the instrumentation for Mossbauer spectroscopy? As we have already discussed, that we will be embedding our source, that is, here we are taking the 57 Fe nuclei in a solid crystal matrix. Both of these will be embedded in a solid crystal matrix to avoid the loss in energy, to avoid the loss of recoil energy. And because of this increase in effective mass, the energy overlap between source and sample is improved. So for example, if you have this source, we have our source, and such that the gamma radiations which are being emitted in the transition from excited state to ground state in the source are not being absorbed by the sample. That is, there is an energy difference between both the transitions. This is for source and this is sample. It shows that the energy which has been emitted by the source is not been absorbed by the sample, and there is a energy gap involved here. So to if we want to avoid this loss of energy, we introduce Doppler Doppler effect. Doppler effect is introduced so that there is absorption of gamma rays emitted by source. So for this, what we are doing is we will moving this sample towards or away from the sample. That is, we will make either source or sample movable. This is detector. So if we say there is no energy overlap between the source and sample, so we will be getting the spectra, that is percentage transmittance versus time. So this energy will be, that is the energy emitted by the source, will be totally transmitted and will be detected by this detector, so that we will get the 100% transmittance, that is no absorption of energy by the sample. This is the case. But when we are moving the source towards the sample, then there will be shifting of this energy band, that is there will be some overlap of energy between energy emitted by the source and the sample, and we will observe a decrease in the percentage transmittance. And if we keep moving our source towards the sample, there will be a time when there will be complete absorption of energy by the sample which was emitted from the source. That is, whatever energy emitted by the source will be totally absorbed by the sample, and we will get zero transmittance. Now, if we say this is case 3, and if this source moves away from the sample, we will reach further a stage where we will get 100% transmittance. So we are basically moving the source away, or towards or away from this sample, so that there is some amount of energy absorption by our sample, and this is the kind of Mossbauer spectra we will observe. And this velocity is generally in millimeter per second. And this velocity change due to Doppler effect will give us idea about the energy absorbed by the sample, such that velocity is function of energy. And this is how we record the spectra for the Mossbauer spectroscopy, which is percentage transmittance versus velocity. or we can say it is generally measuring the number of photons absorbed by the sample which are being emitted from the source. So now we will be looking into the parameters for Mossbauer spectroscopy. So there are four parameters involved. First is number of signals. Second is position of signals. Which is isomer shift defined in millimeter per second. Third is multiplicity of signals. And the fourth one is quadrupole splitting constant. So first is number of signals. How will you find out for a particular complex how many signals in the Mossbauer spectra we will get? So chemically equivalent Mossbauer nuclei present in the molecule will give same signal, and chemically non-equivalent Mossbauer nuclei will give different signal. So the first example is Fe3CO12, and if I draw the structure for this, Mani Ratnam, can you please tell me how many Fe atoms are chemically equivalent in this complex?
Two, ma'am.
Yes. So how many signals based on this we will get?
I don't know, ma'am. Formula, I forget it.
Okay, so as I have written and mentioned that chemically equivalent nuclei will give one signal, and so here we have two kind of iron nuclei involved. So these two are chemically equivalent. For these two, we will get one signal, and for this one, iron at this nuclei, we will get another signal. So for this,
Totally two signal.
yeah, so there are two signals here. And what will be the intensity ratio? For these two, we will get the intensity ratio will be 2 is to 1. Okay,
Okay, ma'am.
uh, I'll take a few more examples for this. This is Fe2CO9. So, can you now tell me how many signals we will get and what will be the intensity ratio?
Two, ma'am.
What?
Two.
Sorry, I missed this. Won't. We will get one signal, as these two nuclei are chemically equivalent, and the intensity ratio, like there will be no ratio then if we are getting one signal.
Okay, ma'am. The same environment is present both Fe. So one signal, we get one signal.
Yeah, right. So if you are given a Mossbauer spectra and you don't know this sample, and you have been told the chemical structure, like this chemical formula you have been told, and you are told that there are two signals, so you will be able to find out what will be the structure of a particular complex. For example, I am writing this example: I2 Br2 Cl4. So this is the unknowns, this is the complex, and you don't know the structure for this. And there are two Mossbauer spectra given for this sample. One has one signal and the other one has two. So will you be able to draw the structure for this complex? I2 Br2 Cl4.
I cannot understand, ma'am. Once again, explain, ma'am.
Okay, so I'm just you are given this. You have been given this complex I2Br2Cl4, and you have two spectras. You recorded the spectra, so you are getting this. If you are getting two signals, so will you be able to draw the structure for this? You just have to maintain the chemical equivalency. Okay, I'm drawing it. You might be able to understand. So you have to arrange the atoms such that both the in both these iodine nuclei are chemically equivalent. So in this,
Yes, ma'am.
you can
Two
see
signal, ma'am.
these are
One signal, one signal.
one. Yeah. So if you arrange it like this, now tell me how many signals you will get. Are these two chemically equivalent now?
No, ma'am. Both are non-equivalent.
Yeah. So this is why this arrangement based on the spectra you can define. Okay.
Okay, ma'am.
So for this we have two
Two signal.
signals. Okay. Now the second is isomer shift.
Uh,
And for this isomer shift, you need to understand the electron nuclear interaction. So, what are the orbitals which are mainly involved in this Mossbauer spectroscopy that we have to find out? And the question here is there any finite possibility that electrons around the nuclei will penetrate the nucleus and will reside in the same place? So, is it possible that electrons and nuclei both are present in the same, like this is nuclei and it is present uh, in this electron cloud? So, is it possible that these electron penetrate the nucleus and reside in the same place?
no, ma'am. S orbital electrons only enter in the nucleus.
Yes. So, you might be following the main lectures. So, here comes this radial density functions rule. Yes. Yes, Tx and Fx. So s orbitals can go through the nuclear interaction as defined by radial density function, radial distribution function. So this radial distribution function, which is probability of finding the electron psi square versus distance from the nuclei, and psi square is probability of finding electron in the orbital. And if you draw the radial distribution function for 1s orbital, you will find out that r at r equal to 0, the probability of finding the electron is non-zero. That is, there is finite probability of finding the electrons that inner shell electrons, 1s orbital, can penetrate the nucleus. But if you draw it for 2s and 2p, at r equal to 0, psi square is equal to 0, which means for 2s electrons can't penetrate nuclei. Similarly, for 2p, r is equal to, for r equal to 0, psi square equal to 0. And if we further discuss this for d and f orbital, this similar pattern is observed, that for r equal to 0, that is when electron is inside the nucleus, the probability of finding electron will be 0. So there is the only condition where the probability of finding the electron is not equal to 0, when it is inside the nucleus. It is possible for the inner orbital electrons, that is 1s orbital electrons. And that's why s orbital is important for Mossbauer spectroscopy. And the origin of isomer shift is difference in electronic environment around Mossbauer active nuclei of source and sample. So electron density in s orbital is the major deciding factor for isomer shift, and the electron density in the p and d orbital will affect the isomer shift by screening the s electron density. So electron density in s orbital is the major deciding factor in isomer shift, whereas electron density in p and d orbital. So this isomer shift delta is equal to a constant multiplied by Re square minus Rs square into delta psi s square, where Re is equal to radius of excited nucleus, that is source nucleus. Sorry, Re is radius of excited state nucleus. Radius of excited, and Rg is radius of ground state nucleus. And this psi Sa is equal to s orbital electron density around absorber nucleus. Basically, this delta is equal to constant multiplied by Re square minus Rs square into psi Sa square minus psi Ss, that is delta is equal to delta R into delta psi s. This psi Ss is s electron density around source nucleus. So for 57 Fe, this delta R value is negative, and so increase in the s electron density around sample, that is absorber nucleus, will decrease the isomer shift, and increase in d electron density will increase the isomer shift. So we will be discussing this part of the isomer shift in the proper details in the next session. uh, if you have any doubts so far, you can ask.
Ma'am, the formula del equal to constant R E square minus R S square means.
This radius of this re square, that is the sample ground state and excited state radius. For example, when radius of excited nucleus by, so when we are if we are removing an electron out of some nuclei, its radius will increase or decrease based on that the okay, I will look into this part. I'm not sure, like I haven't properly gone through the isomer shift part. I will discuss in this in the next lecture properly.
Okay, ma'am.
Anything else you want to ask? In the earlier part, isomer shift, I will be covering from the beginning in the next session. Okay.
Okay, ma'am. Thank you.